Hello, AP Chem students, and welcome to topic 3.2, properties of solids. So the learning objective here is 3.2.a, explain the relationship among the macroscopic properties of a substance, the particulate level structure of the substance, and the interactions between these particles. So again, we're continuing this conversation of intermolecular forces and how that impacts our substances. So let's dive right in. So whoops, got these out of animation order, but that's okay. So recall for a few moments that the three states of matter that we think about in this course are solid, liquid, and gas. Of course, in existence, in reality, there are more states of matter, but that's what we're going to focus on in this course. So particle diagrams look like this. So a solid is tightly packed, close together. A liquid is more spread out. We sometimes see liquids kind of arranging themselves in layers so that they slip and slide past each other. But in reality, the liquids don't really have any kind of definite order to their spacing, but they are in pretty close contact with each other. Not quite as close as solid, as you can see. Also, you should know with solid that sometimes we see a highly ordered structure, like in the shape of a crystal lattice. Sometimes it's more amorphous and it's just kind of powdery. So both of those things exist for a solid. With a gas, we see a huge amount of distance, relatively speaking, between the particles, although that depends on the properties of that substance, so pressure, volume, and temperature. So we're going to think about the properties that are related to the states of matter over the next couple of sections. So the solid and liquid states are called condensed states of matter, and that's because their atoms are very close to each other. So you really can't squeeze them any tighter together because they're already pretty closely packed. Another major difference between solids and liquids versus gases is the presence of IMFs. So these IMFs are what determine the properties of the substances. So again, we assume that solids, or we know that solids and liquids have IMFs present. That is what is holding them together in the condensed state, versus gases, which we assume do not have IMFs at play. And we'll get more into that when we talk about gases. So we're going to think about physical properties for a few minutes and how the IMFs impact those. So what I want you to think about here is if substance A has a property that is in this column relative to that of substance B, then the IMFs of substance A are what relative to substance B, weaker or stronger? So this is a choice here. And then we're going to talk about the reasoning of that. So if substance A has a higher boiling point than substance B, then its IMFs are stronger because stronger IMFs require more energy to be overcome. And so the particles will not escape the surface of the liquid to become a gas until the temperature is higher to give them that extra required energy to do that. If it has a lower boiling point, then of course its IMFs are weaker. So the weaker IMFs do not require as much energy to be overcome. Particles will be able to escape the liquid to become gaseous at a lower temperature, strictly because they don't require that same amount of energy. Higher melting point. If substance A has a higher melting point, then its IMFs are stronger, basically for the same reasoning. Stronger IMFs require more energy to be overcome. I want to pause here and point out that I am specifically saying overcome, not broken. Bonds are broken. Intermolecular or interparticle forces are overcome. Okay? So the particles will require more energy or a higher temperature to spread out and become the liquid. So that's what's happening during melting. Lower melting point, of course, would be the opposite because weaker IMFs do not require as much energy to be overcome. So the particles will be able to spread out into that liquid phase at a lower temperature. So a higher vapor pressure is actually maybe the opposite of what you think. So a higher vapor pressure is weaker. That's because weaker IMFs are more easily overcome, and so particles will be able to escape the liquid surface more often to go into that gaseous phase. So remember that with a boiling point and melting point, we're kind of controlling the temperature there, right? With a vapor pressure, what we're thinking about is if you want to compare things at the same temperature, but this one has a higher vapor pressure, that means that more particles are escaping the liquid surface at that temperature to become a gas. So it's important for you to remember that things are constantly vaporizing. That's in equilibrium, and we'll talk about equilibrium much later in the course. But anytime you have a liquid, there are a certain number of particles that are escaping the surface of that liquid to become a gas. Okay, and we notice this if you were to leave a glass of water sitting out on a table for a really long time, eventually all that water would evaporate. That's vapor pressure. Now, of course, then if you have a lower vapor pressure, that means that those stronger IMFs are at play. And so they're harder to overcome. And so at that particular temperature, the particles will less often escape the surface of the liquid to become gaseous. Okay, so then let's think about types of solids here. So we have ionic, in which case we have strong attractions between positive and negative ions. And this is an image of an ionic solid for you. I'm going a little bit out of order that I wanted to, but that's okay. Then we have metallic solids, which can be alloys. They're held together by a mobile sea of electrons. Okay, and that's kind of the phrasing we like there. This is a little bit of a review from a section that we talked about, I believe, in Unit 2. This is what a metal can look like. Usually they can be packed pretty deep like this, but remember also that metals can be spread out, right? They're malleable and ductile. Then we have two kinds of covalent solids. Let me move my face down here. We have network covalent, which is held together by a network of covalent bonds, and those are relatively strong. And then that network can either be in three-dimensional or two-dimensional layers. And then this is kind of what that looks like. So this is a stronger attractive force than an intermolecular force. This is a bond. So we have overlapping electron clouds and the sharing of electrons between the atoms. So that's what makes network covalent solids very, very distinct in terms of their properties. We're going to talk about properties in just a second. There are four that the AP program wants you to recognize as being network covalent. These four are specifically mentioned. They are not the only network covalent solids, but because they're specifically mentioned in the course and exam description, it helps you a lot if you can recognize these four specifically. So the diamond form of carbon is one. Silicon dioxide, SO2, is another one. Silicon carbide, SiC, and then the graphite form of carbon. So these, all four of these are examples of network covalent solids. Then we have molecular solids, which are still covalent molecules, but they're held together by van der Waals forces. So instead of seeing this network of covalent bonds even between the molecules themselves, you actually have just the distinct molecules that are being held together by van der Waals forces, which you may recall are relatively weak IMFs. So that makes network covalent and molecular solids very different in terms of their properties. So let's examine properties here. So in the ionic compounds, we see that we have a low vapor pressure, a high boiling point, and a high melting point. They are, and this is a big thing down here. The high boiling and melting points are important with ionic. And another thing that is very indicative of an ionic solid is that they're not conductive in the solid form, but they are conductive when you melt them or dissolve them in water. And the reason for that is that in solid form, they're packed, right, in these rigid crystal structures where you've got the positive and the negative that are self-assembling. And so those are not mobile charges when they're in their solid form. But as soon as you melt them or dissolve them, then those charges can move, and that's when they become conductive. Because remember, to be conductive, you have to have mobile charges. So metallic solids have a low vapor pressure. The melting and boiling point of metallic solids can vary, especially if you make it an alloy. But they're a very indicative thing here is that they're conductive in solid form. So that's how you would distinguish an ionic compound from a metallic compound. And that, again, is due to that mobile sea of electron. You have the mobile charges. Network covalent solids have low vapor pressure, high boiling and melting points. Those would be very, very high. But they are non-conductive, and that is because you have this series of bonds that are holding them together. And again, you do not have mobile charges, so that makes them non-conductive. Okay, so then your molecular solids, because they're held together by van der Waals forces, actually have a vapor pressure that's generally higher because, again, it's easier when we get into the, if you melt them and they get to the liquid phase, then they would be able to vaporize. The boiling point is usually, this is incorrect. I should have changed this. The boiling point is often low for molecular, and the melting point is also low. And they are so low that we often see them existing in the gaseous form instead of becoming a solid. Okay, so let me actually change that real quick. Okay, so there we go, low boiling point. All right, so moving on along, talk about polymers for a second. So sometimes molecular solids, right, so not the network covalent, but molecular solids will self-assemble to form something called a polymer. And so a polymer is a large molecule that's made up of repeating units. And these repeating units are called monomers, and then they come together to be polymers. So a monomer looks like this. It's a small molecule. And then that molecule kind of self-assembles, and then they click together, almost like Legos, to make a polymer. And so the polymer is the long chain molecule that's made up of the repeating pattern of polymers. And so they can actually control the size of the polymer, usually by just using a reaction time. So they'll let it react for a certain amount of time, and then they'll introduce something into the system that quenches that reaction. It's usually kind of like an end cap, if you want to think of that. And so you would just, stick something on, introduce something into the system that sticks onto the ends and then stops the polymer from assembling. So some examples include plastics, cellulose, and carbohydrates. There are many others. That's just a few examples off that you are probably familiar with. Polymers not only have many uses in synthetics like plastics and fabrics, but also in biology. So proteins are biological polymers made up of the monomer units, amino acids. And then, so that looks like this, right? So here's an amino acid, and then they can self-assemble into proteins like that. So that's a biological example of a polymer. We also see polymers with DNA. DNA is made up of the monomers that are nucleic acids. Okay, so what should I be able to do with this? So first of all, identify the type of a solid, either given the formula, or more often we see properties and then asked to identify the solid based on the properties. Use IMFs, or interparticle forces, present in pure substances to explain why physical properties such as melting point, boiling point, and vapor pressure might vary between the two named substances. And then use representations of ionic, molecular, metallic, and network covalent solids to justify their properties, thinking about those mobile charges, the packing, things like that. Compare and contrast the properties of ionic, molecular, metallic, and network covalent solids. So that would be things like hardness, whether or not it would have a low boiling point or a high boiling point or a melting point or anything like that. If it would fracture if you were to hit it, or if it might spread out. So that would be the difference between ionic and metallic, things like that. So that is it for section 3.2, and I'll see you soon for section 3.3.